Welcome back. Now that we've covered the physical and data link layers, next we need to step through layer 3 of the OSI model, which is the network layer. As I've mentioned in previous videos, each layer of the OSI model builds on the layers below it, so layer 3 requires one or more operational layer 2 networks to function. The job of layer 3 is to get data from one location to another. When you're watching this video, data is being moved from the server hosting the video through to your local device. When you access AWS or stream from Netflix, data is being moved across the internet, and it's layer 3 which handles this process of moving data from a source to a destination. To appreciate layer 3 fully, you have to understand why it's needed. So far in this series, I've used the example of 2 to 4 friends playing a game on a local area network. Now, what if we extended this? So now we have 2 local area networks, and they're located with some geographic separation. Let's say that one is on the east coast of the US and another is on the west coast. So there is a lot of distance between these 2 separate layer 2 networks. Now, LAN 1 and LAN 2 are isolated layer 2 networks at this point. Devices on each local network can communicate with each other, but not outside of that local layer 2 network. Now, you could pay for and provision a point-to-point link across the entire US to connect these 2 networks, but that would be expensive, and if every business who had multiple offices needed to use point-to-point links, it would be a huge mess and wouldn't be scalable. Additionally, each layer 2 network uses a shared layer 2 protocol. In the example so far, this has been Ethernet. Any networks where we're only using layer 2, if we want them to communicate with each other, they need to use the same layer 2 protocol to communicate with another layer 2 network. Now, not everything uses the same layer 2 protocol. This presents challenges because you can't simply join 2 layer 2 networks together which use different layer 2 protocols and have them work out of the box. With the example which is on screen now, imagine if we had additional locations spread across the continental US. Now, in between these locations, let's add some point-to-point links. So we've got links in pink which are cabled connections, and these go between these different locations. Now, we also might have point-to-point links which use a different layer 2 protocol. In this example, let's say that we had a satellite connection between 2 of these locations. This is in blue, and this is a different layer 2 technology. Now, Ethernet is one layer 2 technology which is generally used for local networks. It's the most popular wired connection technology for local area networks. But for point-to-point links and other long-distance connections, you might also use things such as PPP, MPLS, or ATM. Not all of these use frames with the same format, so we need something in common between them. Layer 2 is the layer of the OSI stack which moves frames. It moves frames from a local source to a local destination. So to move data between different local networks, which is known as internetworking, this is where the name internet comes from, we need layer 3. Layer 3 is this common protocol which can span multiple different layer 2 networks. Now, layer 3, or the network layer, can be added onto one or more layer 2 networks, and it adds a few capabilities. It adds the Internet Protocol, or IP. You get IP addresses, which are cross-networking addresses which you can assign to devices, and these can be used to communicate across networks using routing. So the device that you're using right now, it has an IP address. The server which stores this video, it too has an IP address. And the Internet Protocol is being used to send requests from your local network across the internet to the server hosting this video and then back again. IP packets are moved from source to destination across the internet through many intermediate networks. Devices called routers, which are layer 3 devices, move packets of data across different networks. They encapsulate a packet inside of an Ethernet frame for that part of the journey over that local network. Now, encapsulation just means that an IP packet is put inside an Ethernet frame for that part of the journey. Then when it needs to be moved into a new network, that particular frame is removed and a new one is added around the same packet and it's moved on to the next local network. So as this video data is moving from my server to you, it's been wrapped up in frames. Those frames are stripped away, new frames are added, all while the packets of IP data move from my video server to you. So that's why IP is needed at a high level, to allow you to connect to other remote networks, crossing intermediate networks on the way. Now over the coming lesson I want to explain the various important parts of how Layer 3 works, specifically IP, which is the Layer 3 protocol used on the internet. Now I'm going to start with the structure of packets, which are the data unit used within the internet protocol, which is a Layer 3 protocol. So let's take a look at that next. Now packets in many ways are similar to frames. It's the same basic concept. They contain some data to be moved and they have a source and destination address. The difference is that with frames both the source and destination are generally local. With an IP packet the destination and source addresses could be on opposite sides of the planet. During their journey from source to destination, packets remain the same. As they move across Layer 2 networks, they're placed inside frames, which is known as encapsulation. The frame is specific to the local network that the packet is moving through and changes every time the packet moves between networks. The packet, though, doesn't change. Normally, it's constant for the duration, for its entire trip between source and destination, although there are some exceptions that I'll be detailing in a different lesson when I talk about things like network address translation. Now there are two versions of the Internet Protocol in use. Version 4, which has been used for decades, and version 6, which adds more scalability, and I'll be covering version 6 and its differences in a separate lesson. An IP packet contains various different fields, much like frames that we discussed in an earlier video. At this level, there are a few important things within an IP packet which you need to understand, and some which are less important. Now let's just skip past the less relevant ones. I'm not saying any of these are unimportant, but you don't need to know exactly what they do at this introductory level. Things which are important though, every packet has a source and destination IP address field. The source IP address is generally the device IP which generates the packet, and the destination IP address is the intended destination IP for the packet. In the previous example we had two networks, one East Coast and one West Coast. The source might be a West Coast PC and the destination might be a laptop within the East Coast network, but crucially these are both IP addresses. There's also the protocol field, and this is important because IP is Layer 3. It generally contains data provided by another layer, a Layer 4 protocol, and it's this field which stores which protocol is used. So examples of protocols which this might reference are things like ICMP, TCP, or UDP. If you're storing TCP data inside a packet, this value will be 6. For pings known as ICMP, this value will be 1. And if you're using UDP as the Layer 4 protocol, then this value will be 17. This field means that the network stack at the destination, specifically the Layer 3 component of that stack, will know which Layer 4 protocol to pass the data into. Now the bulk of the space within a packet is taken up with the data itself, something that's generally provided from a Layer 4 protocol. Now lastly, there's a field called time to live, or TTL. Remember that packets will move through many different intermediate networks between the source and the destination, and this is a value which defines how many hops the packet can move through. It's used to stop packets looping around forever. If for some reason they can't reach their destination, then this defines a maximum number of hops that the packet can take before being discarded. So just in summary, a packet contains some data which it carries generally for layer 4 protocols. It has a source and destination IP address. The IP protocol implementation which is on routers moves packets between all of the networks from source to destination, and it's these fields which are used to perform that process. As packets move through each intermediate layer 2 network, it will be inserted or encapsulated in a layer 2 frame specific for that network. A single packet might exist inside tens of different frames throughout its route to its destination, one for every layer 2 network or layer 2 point-to-point link which it moves through. Now, IP version 6 from a packet structure is very similar. We also have some fields which matter less at this stage. They are functional, but to understand things at this level, it's not essential to talk about these particular fields. And just as with IP version 4, IP version 6 packets also have both source and destination IP address fields, but these are bigger. IP version 6 addresses are bigger, which means there are more possible IP version 6 addresses. And I'm going to be covering IP version 6 in detail in another lesson. It means though that the space taken in a packet to store IP version 6 source and destination addresses is larger. Now, you still have data within an IP version 6 packet, and this is also generally from a layer 4 protocol. Now, strictly speaking, if this were to scale, then this would be off the bottom of the screen, but let's just keep things simple. We also have a similar field to the time to live value within IP version 4 packets, but in IP version 6, this is called the hop limit. Functionally, these are similar. It controls the maximum number of hops that the packet can go through before being discarded. So these are IP packets. Generally, they store data from layer 4, and they themselves are stored in one or more layer 2 frames as they move around networks or links which form the internet. Okay, so this is the end of part 1 of this lesson. It was getting a little bit on the long side, and I wanted to give you the opportunity to take a small break, maybe stretch your legs or make a coffee. Now, part 2 will continue immediately from this point, so go ahead, complete this video, and when you're ready, I'll look forward to you joining me in part 2.